All right, so then this one. Page 88. All right, so this is one of those cases where we need the sign chart, we need some coordinates, and from there we have to come up with a graph. All right, I mentioned when we went over the problem that preceded this one that this one was way easier. The one that we did in class was the crunchy one. All right, this is easier because it has, or at least in terms of getting a sense of the shape of the graph, it has a vertical asymptote at 2 and also at -2. So x equals plus or minus 2. So you already have two benchmarks right off the bat. All right. The parentheses on the bottom, I don't know why I put them there.
Do we need to, can we just state that the asymptotes there, do we need to like prove it by saying that it's not standard equal to 0?
You do not need to prove it. So that's good news. Because, I mean, in this case, it's not bad. But, I mean, there are some cases where it gets funky. I mean, if it had cosine on the bottom, I don't want you to have to show the work. And nobody does. There's no knowledge penalty. So if you know that cosine is equal to 0 at -pi/2 and pi/2, then there's no need for you to pre-calc your way through that solution, right? So there's some things that we can call prior knowledge at this point, all right? Yeah, so if somebody wants to claim that as a typo, the parentheses on the bottom, I don't know why I put them there. They need to be there on the top, but on the bottom, there's valid reason. And in fact, it bothered me so much, I'm rewriting the problem so that they're not there. All right, so x-intercepts, and technically I guess they didn't need to be there on the top, it's just, it would be a different problem, but x-intercepts, x equals plus or minus 3. Y-intercept, if you can get a y-intercept, that's a good thing. All right, so in this case, we're looking at -18 over -4. So y would be equal to 9/2. Just plug in a 0 for x. All right, so it gives us some benchmarks on the graph. That's what we're looking for. Never hurts to state the domain. Negative infinity to -2, union -2 to 2, union 2 to infinity. All right, it gives you a sense of direction. You're going to have to make a sign chart that contains these values to some extent. So stating it will kind of reinforce in your own mind that these are the values you're working with. Because they didn't restrict the domain on us like the last problem that we did. So anyway, by indicating that there are vertical asymptotes and restricting our domain, I don't have to state that it's continuous and differentiable or not continuous and differentiable because it's implied. If I'm restricting my domain, I'm essentially stating that it's not continuous everywhere, therefore it would not be differentiable everywhere. All right, so it never hurts to put it in if you feel like you don't want to take the chance, but it's implied, so it's fine. So we took care of that. Symmetry you can look at, whether it's an even or odd function. If you're looking at even versus odd, there's a couple of ways to handle it. One would be just to look at all the powers of your exponents, right, on the right-hand side. So if you look at all these powers, you can see that every single power is an even power. All right, so x squared, after each constant, there's an implied x to the 0th power. 0 is an even number. So we're looking at an even function. If you don't like that, replace every x with a negative x, simplify, you get the same expression, therefore even function. All right. The reason why that's beneficial, so even function tells us that it's symmetric over the y-axis. If it were an odd function, meaning all the powers were odd, then it would be symmetric through the origin. Gives you a sense of what the graph's going to look like. So now going into the problem, bless you, I know that there are going to be two asymptotes, and I know it's going to have symmetry over the y-axis. So it's going to limit the amount of calculations I have to do in order to come up with my solution. But we do have to take a derivative. In this case, I think it might serve a purpose to distribute through the two. Before taking our derivative. All right, so a little low D high action. X squared minus 4 times 4x minus the high d low. The d low will be 2x. So I'll just write it as 2x squared minus 18 times 2x over the denominator squared. All right, we need critical values, which means we have to set this equal to 0 and solve, but if we can clean it up first, that's in our best interest. All right, so let me just double check my derivative. Okay, looks good. So I don't have a common x squared minus 4 across the board. That would be great if I did, because then I could cancel it with part of the denominator. If I go through the critical values, we set the numerator equal to 0, set the denominator equal to 0. If we set the denominator equal to 0, then we're just going to get one of the asymptotes, so that's irrelevant. We don't have to worry about it. On the top, distributing is a technique that you could use, but it's not the best technique generally. The best technique is to look for a common factor. On the top, I can pull out definitely a 4x, which would leave us with an x squared minus 4 minus x squared minus 9. I left it in parentheses, so I'll get that in a minute. So I left this in parentheses, took a 2 out of here, put it with that, brought the 4x out of the whole thing. Sometimes, very rare instances, it doesn't clean up as well as you would like, but in almost every other case, it'll clean up very nicely.
Yeah. Could you just distribute 4x and 2x, and when you get to 4x cubed, so it just cancel out?
Yes. In this case, equal level of difficulty roughly, but in, I would say, 90% of other cases, that's going to make the problem more difficult. All right, so generally factoring out something in common is going to make your life a lot easier. All right, so it's one of those things like believe it, don't believe it. Now, eventually you'll believe it. All right, so the x squares will cancel. Negative 4 plus 9 will give you a 5, right? So actually, let me just put it all together. So 20x on top. And that would be my first derivative. Bless you. My critical value then would be x equals 0. All right, you get that by setting the top equal to 0 and solve it. Okay. So there's some calculations that just don't need to be shown. Because when we rewrite this set it equal to 0 just to show you that 20x equals 0, no, I'm not doing that. And you don't have to do that either. All right, so then we go for our second derivative. And we hope that things don't get out of hand too much. So low D high would be 20 times x squared minus 4 squared minus the high, so 20x, d low, so that would be 2 times the inside stuff times 2x, so 4x times the inside stuff. And that would be to the 4th on the bottom. I don't know if this quite proves my point, but it's a step in the right direction towards what I was saying a few moments ago, where pulling something out tends to make your life a little bit easier, because while x squared minus 4 squared is not the craziest thing to distribute out, it's something that you're less inclined to do than maybe in the first derivative, right? So I have an x squared minus 4 that's common to each term, so we factor it out and cancel it. So meh, 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 3 minutes. All right. I could pull out a 20, but I don't see the benefit of doing that because it's just a constant. So I'll go the other way and make a 20x squared minus 80 minus 80x squared over x squared minus 4 cubed. So then my second derivative would clean up somewhat to negative 60x squared minus 80. It's quadratic in binomial form. That's not terrible. So when I'm looking for my points of inflections, I mean, they're not going to be the nicest numbers ever, but you'll be able to get them relatively easily. So set the top equal to 0 because for second derivative, can't emphasize this enough, we don't need to know where it's undefined, we just need to know where it's equal to 0. All right, first derivative, I need to know both, right? Or at least have a sense of both. Second derivative, just where it's equal to 0. All right, so we're looking at 60x squared equals 80. Actually, negative 80, right? So then nothing after all that, because I would divide, take the square root of a negative, so I'd only get imaginary solutions. All right, we're living in the real world for this particular unit. All right, so could have been a lot worse. Could have had some, if it were 60x squared equals 80, 4/3, so 2 over rad 3, so oof, 2 radical 3 over 3, if you rationalize, I don't know why you would, but that would make its way into the sign. Oh, gross. All right, but after all that, you can now eliminate a point of inflection as a possibility here. All right, so if there is a change in concavity in the graph, and this is something you have to kind of think about, there can still be change in concavity without there being points of inflection, because perhaps your asymptotes are serving as that change, whereas concave down prior to an asymptote, concave up after the asymptote. Can't be a point of inflection if there's no point there, right? So the asymptotes might serve as the point of inflection, or maybe there's simply no change in concavity. That could be a possibility too. The good news is, at least as far as the sign chart is concerned, I can ignore everything related to my second derivative, because as we learned in the last problem that we did, we can get the signs of our second derivative, or at least a sense of them, just by knowing where the critical values and the relative extrema are. So if I could identify my relative extrema and I know where my asymptotes are, then I can kind of backfill my second derivative stuff without looking at my not too terrible second derivative once it's simplified, but I still don't want to have to do it. That's the whole point. All right, so sign chart action. All right, so x, f prime, double prime, conclusion, negative infinity to negative 2, negative 2, negative 2 to 0, stop, take a look around at 0, 0 is next, yeah, 0, 0 to 2, stop, take a look around at 2. And then 2 to and finish here. Draw some shaky lines. Right. There's a 20? There was a 20x.
Oh, and it was 0. Sorry.
And it was 0.
Oh my god, I don't know why I wrote 0. 20 instead of 0.
Okay, so I know at -2 and 2 I have vertical asymptotes, so I could draw that conclusion immediately. I mean, I already drew it. So. At 0, it's a critical value, so I'm assuming there's some sort of turning point there. We're not going to assume for long because we're going to verify it, but we'll take a quick look. And around those asymptotes, something has to be going on. The good news is my first derivative is very easy to evaluate because the numerator drives the whole thing. Right? Denominator's got to be positive because anything to the second power, anything to an even power has to be a positive number. So if I plug in a negative for my x value, I'm going to get a negative derivative. If I plug in a positive, I'll get a positive. All right, so no calculation required. Anything left of 0 is going to be negative. Anything right of 0 is going to be positive. So it goes from decreasing to increasing. All right, so I know now it's down then up, so I'm looking at a relative minimum at 0. All right, which is great news. And it's going to help us make a determination of concavity. All right, because now the asymptotes kind of make things a little wonky, but I do know for the intervals immediately surrounding my relative minimum, got to be concave up. Otherwise, you could not have a relative minimum there. It's got to be upward facing. So positive signs. All right. The issue is we don't really know what's going on beyond the asymptotes. However, and this is the good news, more good news. There's so much good news in this problem. Since we know it's an even function and symmetrical, whatever's happening to the left of -2 is going to also happen to the right of -2. If it's concave down to the left, it'll be concave down to the right. Same thing if it's up. All right, so all I need to do is figure out one of them, and I got them both. We can't assume that there's a change in concavity just simply because there's a vertical asymptote there. All right, so what we need to do is pick a nice convenient value. Now it's less than -2, so how convenient can it be? But a convenient value that's either less than -2 or more than +2. All right, so we'll go to the right-hand side. At least it's positive numbers. So if I plug in a 3, for example, or a 4, whatever you want, it's going to be very negative on the top, right? Yeah, so whatever I put in there, no matter if it's positive or negative, it's going to be very negative on the top. If I plug in something bigger than 2 on the bottom or smaller than -2, you're looking at something that's positive. Positive cubed is positive. So no matter what I plug in for x, top or bottom, it's going to be very negative on the top, positive on the bottom, so it's got to be negative. Negative divided by positive is negative. All right, so again, in terms of the calculations, are we really calculating? The point is that we shouldn't have to. All right, just making a determination of the nature of the numbers should be enough. All right, concave down, concave down. All right, so if I could figure out my minimum point, then I'll be in pretty good shape because I could pretty much estimate everything else. So what I would do is I'd go back to my original function and plug in a 0 for x, but fun fact, I've already done that. That was my y-intercept. So I'm going to have x-intercepts at plus or minus 3. asymptotes at plus or minus 2, the graph pretty much draws itself. All right, so let's get some asymptotes there. (9/4). So that's a little bit more than 2, right? 2 1/4. Is it 9/2? Oh, it's 9/2. Ah. So 4 1/2. Oh, I undoed too much. And we know it's concave up in that interval, so, because it's a min. It's concave down beyond the vertical asymptotes. We did find the vertical asymptotes. Maybe it would be a good idea to find a horizontal asymptote. In this case, the horizontal asymptote would be what? 2, yeah. And the powers are the same, ratio of the coefficients. You don't have to show the limit work. Just to at least get a sense of how high it's going to go. So I know it's going to be concave down. So it's got to look something like this. The pre-calc version of this kind of problem was find your asymptotes, find your intercepts, x and y intercepts, maybe find end behavior if you needed to, which would be the same as horizontal asymptotes in this case, and then test a bunch of x values to see what's going on. Here, we actually want to find the extreme values if they exist, but in the grand scheme of things, the only thing that makes this challenging, really, without a calculator, would be that bad boy right there. And it's not really challenging to construct a sign chart. It's just tedious, I'll give you that, but also it does take a little bit of thinking, because you could always come up with the results. You could always come up with the signs through rote calculation. Our purpose is to try to avoid having to do that. We don't want to have to do the rote calculation, because you know the story. You're not going to have a calculator all the time. And even a problem like the one on the previous page that took the whole page, don't expect to have a calculator for that kind of question. This question, the same deal. All right, so very important to keep your eye on the prize here. All right, well, my plan of giving you time to work on your project did not work. So let me talk about